Hello, continuing on from the previous first lesson of differential calculus. We have learned about many different things in the first lesson. First, the average rate of change, to the connection of the instantaneous rate of change, which was really directly connected to the definition and the identity of the first principles, and also known as the differential coefficient. So, let's just begin with a little recap of what we did from the previous lesson. So, first, the average rate of change. So the average rate of change was basically calculated by first selecting an interval that we wanted to calculate the average rate of change from. For the example that has already been shown on the board, let's say that I wanted to calculate the average rate of change between the intervals a and x. Then it could be simply calculated by simply connecting the endpoints of the intervals of the point a and x on the function y equals fx, and connecting these points and calculating the gradient of the lines that you connected from. However, then what about the instantaneous rate of change? Well, instantaneous rate of change is basically calculating a gradient at a single point in which the function goes by, also known as the tangent line. The instant gradient in which that can be drawn from the point where the function travels to. So therefore, the yellow line that has been drawn from this function y equals fx at point x equals a can be represented as a definition of the instantaneous rate of change at x equals a. And how can this be calculated? Well, we use the concept of the average rate of change. First, we grab the line of x equals a, which we want to calculate the instantaneous rate of change from. And then we grab another point, a free point of x comma fx that could travel on any point of fx as long as it was on a domain where the fx could be defined. So then we calculated the average rate of change between the two variables a and x. However, not just simple average rate of change, we brought this x infinitely closer to a. And what did we see? We saw that the average rate of change between a and x first started very steep, however, gradually flattened out to get infinitely close to the instantaneous rate of change of x equals a of the function y equals fx. And how did we put this in the limit equation? Well, this here was the formula for the instantaneous rate of change at x equals a, right? When x approaches infinitely closer to a and the average rate of change. However, we said, this was the confusing part, that x could not be exactly a, although it is infinitely getting closer to a, because imagine that you plug in a to both the denominator and the numerator, then you will be able to see that both the denominator and the numerator will yield 0. Since it is 0 over 0, the number will not be defined and will be able to have millions of infinites of different results. Therefore, not being able to converge it into a fixed value of f prime a, also a symbol signifying the instantaneous rate of change at x equals a. Therefore, however, by putting this limit equation, things are made kind of different, because this limit equation suggests that the destination of what this equation, this average rate of change between a and x is actually approaching to. Since, although x cannot exactly be a, since the limit suggests the destination in which this equation is infinitely getting close to, although it cannot exactly be the same, we can confidently say that the destination in which this equation is approaching to is f prime a, the instantaneous rate of change at x equals a. And this data, this instantaneous rate of change at x equals a, could also be manipulated into the same equation of this equation, where instead of x we use h as a variable, h which is a connotation for delta x, the distance between a and x. And actually, I told you, even though we derived this equation first, this equation was the more prevalently or widely used term, also known as the first principle or the differential coefficient. So yeah, that was a brief recap of what we did on the first lesson. And I was actually supposed to put this on the first lesson as well. However, the lesson was getting a little more tedious and long. So that's why I moved it to today's lecture. But however, today's lecture will be very, very short because we are going to be going over a very similar, however, a simple topic, which we are going to delve more into the limit concepts of how we define the first principles. So yeah, without any words, let's begin. So from what we've learned for the short unit of the limits and the continuity lesson, we have said for the limit to exist, for example, for the limit when x approaches to a to exist, then it must satisfy the two extra conditions. There's two separate conditions in which when x can approach a from the positive side and when x approaches a from the negative side. So the limit from these both two conditions when plugged into this equation should yield the same results for this entire limit to exist. And it works the same thing for when h approaches 0 as well. So for the entire limit h approaches 0 to exist, then the limit when h approaches 0 from the positive and the negative side should both have the same values for this entire limit to have the same results. And I'm going to say this right now. So in this equation, right? And for this limit to exist, let's say if this limit exists, right? Let's say if these limit exists, then it means that f prime a also exists, right? And if f prime a exists, f prime a stands for the instantaneous rate of change, or the instantaneous gradient at x equals a of the function y equals fx. And this instantaneous rate of change at x equals a is shown through the yellow line that has been drawn. And you can see that the yellow line is clearly visible, meaning that it exists. If this f prime a exists, it means that the limit also exists, meaning if this limit exists and f prime a exists, we mathematically can say that at fx, the function fx is differentiable at point x equals a. Differentiable, well, that's how you represent it. So once again, let's say that if f prime a exists, or the first principle or the differential coefficient at x equals a exists, then we, in the actual professional language of mathematics, we can say at x equals a, fx is differentiable, which stands as, well, another word for it, f prime a exists, or the first principle exists. Yeah. So I'm sorry for the little bit of confusion. However, let's just go on. So I've previously said for this limit to exist that it must satisfy the two conditions in which the x approaches the variable from both the positive and the negative side, right? So you can vividly see that the yellow line exists here, which means that the instantaneous rate of change exists. This literally signifies that the f prime a exists, also implicitly saying that the first principles also exist. This means that this implicitly also says that the limit in which the x approaches a from the positive side is also the same with the value when x approaches a from the negative side. So on the previous lesson, we have calculated the instantaneous rate of change of the function y equals fx at x equals a when x approaches a from the positive side, right? Then, by saying that this limit exists, then we can confidently say that when x approaches a from the negative side, then the average rate of change between these two variables, when x also infinitely approach a, will also yield the same instantaneous rate of change to the gradient of the yellow line, just like when x approaches a from the positive side. Okay, so we can say that, and you will be able to see, if you actually calculate it yourself, the average rate of change between a and x when x approaches a from the negative side, and you bring x infinitely close to a, and keep calculating the average rate of change, you will be able to see that this gradient infinitely approaches the yellow line here. The gradient of the yellow line. Okay, so, and just a little more fact, I've said that these two equations are the same thing, right? So since they all have the two conditions, let's see the connections between each case on what this case will correspond to and what this case will correspond to. So x approaching a from the positive side is very simple, right? So x is directly approaching a from the positive side. However, what about when h is approaching 0 from the positive side? Well, this is a little difficult to understand, right? However, there is no need to feel the difficulty because I have written the definition of h right here. H could be represented in the change of x, which also signifies the distance between the two variables a and x. And by meaning, I'm first interpreting by ignoring the plus and minus, by meaning that the distance between the a and x is approaching 0, it literally means for us to calculate the instantaneous rate of change at x equals a, then x must infinitely get closer to a, right? It means that the distance in a and x will infinitely get smaller, meaning that their distance will infinitely approach 0. And what does it mean by approaching 0 from the positive side then? Well, then for the distance to be always approaching 0 from the positive side, it means that the distance must start from the positive side and decrease to approach 0 from the positive side, right? So therefore, x must be bigger than a so that their initial distance, delta x, could be initially positive. And in this case, as x infinitely approaches a, as it constantly decreases, it will generally, since it started from the positive value, it will approach 0 from the positive side. However, vice versa, when x is on the negative side of a, the distance between x and a is negative, right? As you can see from this equation, that x is smaller than a, so the initial delta x, the distance between a and x will be negative. Therefore, since it is approaching 0 from the negative value and never becomes positive, because x always approaches a but never goes beyond a, right? So x is always smaller than a. So therefore, the delta x will always start from negative and approach 0 from the negative side. So you can see from the arrows drawn on this diagram here, on this demonstration here, that x approaching a from the positive side corresponds to the case when h approaches 0 from the positive side, and the vice versa from the negative sides as well. So you can see that there are no need to be confused between the connections between when the instantaneous rate of change was expressed in this format or this format. Okay? Sounds good. And finally now, since I've mentioned the case, for this limit to actually exist, then this may probably instigate your inquisition about, oh wait, since you've explained the case for this limit to exist, then is there any conditions for this limit to not exist, the limit of the instantaneous rate of change to not exist? And I'm happy to say that there is. So, but first, let's think about it. What does it mean to say that this limit cannot exist? Well, I said initially that the limit could be calculated, for the limit to exist, then it must satisfy the two conditions. One, approaching a certain value from both positive and negative side. Both limits should have the same value, right? And however, for the limit to not exist, for the limit to not exist, then these conditions, the limit when x approaches a from the positive side and the condition when x approaches a from the negative side, they should not be equal with one another. If they are not equal with one another, they will never exist, right? So let's consider the case in which when the limit of the instantaneous rate of change when x approaches a from the positive side and the case when x approaches a from the negative side is not same with one another. Although it may be hard to imagine, it is actually very easy to think of and draw once you first know it. So I'll first draw an equation. I'll first draw a function. A hideous looking function here. I'll name it a, and I'll name this function y equals gx. And then let's say that I want to calculate the instantaneous rate of change at x equals a. Well, first I can probably make up a guess, like, I don't know, like the left side is negative and the right side is positive, so maybe averaging out the instantaneous rate of change at x equals a, maybe like, I don't know, like a little positive line or little negative or exactly 0. Let's just assume that. However, mathematics is about certainty. We cannot just assume something. We have to see whether it actually is true or not through the mathematical deduction. So let's consider the cases for us to certainly ensure that this limit exists or does not exist. Then we must take consideration of the two conditions here. First, when x approaches a from the positive side, and second, when x approaches a from the negative side. So let's first consider the case when x approaches a from the positive side. So in this case, x should be on the positive side of a, right? And then let's bring this infinitely close to a. Well, although I did not represent it, this equation is linear. This equation seems linear, so therefore, the average rate of change between a and x, even though I bring x infinitely close to a, it will always have the same gradient as this linear equation here. Because basically, even though x infinitely change closer to a, since this itself is a linear equation, the average rate of change of the linear equation is always the same. So therefore, the instantaneous rate of change when x approaches a from the positive side will also have a positive gradient, which is same with the linear equation on the right side of a. So on the right side, it will have an equation like this. It will, on the right side, when x approaches a from the positive side, then the instantaneous rate of change at x equals a will have a positive gradient, right? Then for this limit to exist, then when, let's say then x approaches a from the negative side, then it must also have a positive gradient that is the same with this gradient, right? Now let's try it. First, initially, I'll draw with a yellow line. This gradient, the average rate of change between a and x when x approaches a from the negative side, initially, however, starts with a negative value. And therefore, however, even though x infinitely approaches a, you can see that this negative value, this negative gradient becomes more and more steep, more and more negative. However, because we are calculating the instantaneous rate of change when x approaches a from the negative side, we do not have any information about the positive side of a. So therefore, just knowing the a and the negative side, there is no way that the average rate of change between a and x can be positive. So therefore, the instantaneous rate of change at x equals a will approach a very negative value, which will be very different with the case when the instantaneous rate of change when x approaches a from the positive side, which yields a positive value. Therefore, you are directly able to see that these two conditions, these two limits are not same with each other. These two limits yield a different value. Since for this limit to exist, both limits should yield the same value, however it does not, we can say that this limit does not exist. Therefore, since this limit does not exist, the first principle does not exist, and the f prime a does not exist. And we said on the beginning part of the lesson that if this limit exists, if the differential coefficient exists, if f prime a existed, then we said that at x equals a, fx could be differentiable. Fx is differentiable. However, in this case, in this weird looking function here, we saw that this limit did not exist because when x approached a from the positive side, it yielded a positive gradient, it yielded a positive value. However, when it approached a from the negative side, it yielded a negative value. Therefore, since this limit did not exist, we can say that the first principle and the differential coefficient does not exist, and also that f prime a does not exist. And we said that fx was differentiable at x equals a if f prime a existed, right? However, since the f prime a does not exist at x equals a of function gx, then we say that at x equals a, the function gx, y equals gx is not differentiable. That's how you interpret it in the function. Okay, so that was a pretty long lecture, although I said it was going to be short. But right before we end the lecture, don't you actually have a curiosity? Because in this function of y equals fx, the limit of the instantaneous rate of change at x equals any value could exist if you draw it in a line. However, in this value, we saw a case in which this limit, the instantaneous rate of change, did not exist at all. So how do we distinguish this in a pattern? Well, this case, we had a value, and while we thought maybe the instantaneous rate of change at x equals a on this function here could be, like a linear graph or a very flat positive or negative graph, it actually did not exist because the limit did not exist, right? So how do we know whether the differential coefficient or the first principle or the instantaneous rate of change at a point of a function exists or not? Well, let's more analyze this pattern then. In this graph here, we saw that at the vertex, the function was not differentiable, right? Then let's try a function in which it also contains a vertex. So let's try these two parts. Well, what are the main differences that you see? What are the main differences that you see on these two functions? On the vertex of these functions? Well, if you are pretty intuitive enough, you will be able to see that this vertex has a smoothly connecting gradient. right? It starts from negative, becomes less negative, crosses 0, and then smoothly becomes positive. However, by looking at this part here, by looking at this function, it starts negative. It is constantly negative. However, it drastically suddenly becomes positive without crossing the boundary of 0, without crossing the critical boundary of 0. So that is the biggest problem here, right? However, this case is similar to this case here, where the gradient suddenly changed from negative to positive. And that's why this non-smooth connection of the gradient, although these both functions are continuous, resulted in a different value of the instantaneous rate of change when x approached a from both negative and the positive side. Because let's imagine when x approaches a from the positive side, then it thinks, since it does not have the information from what is on the left side, it always imagines the function to contain a negative value. However, vice versa, when x approaches a from the negative side, it does not have any information of what kind of function lies on the positive side of a. So therefore, just by interpolating by the ranges that it have, the domain that is smaller or same as a, it will always expect the xa to have an instantaneous rate of change, the instantaneous gradient of a negative value. So therefore, that is why these limits differ instead of this case. In this case, this is smoothly related to each other, right? There is no drastic change between the gradients, so the interpolation that the instantaneous rate of change makes at x equals a is correct for both cases when x approaches a from both positive and the negative side. So that is the greatest difference between these two functions here. So now, whenever you see a function where it has a vertex, well, I'm not sure if I can say it in a vertex, but whenever you see a function that has, even though it is continuous, that is very sharp, that has a drastic change in the gradients, that is the drastic change in the gradient at a certain value of a, then you will be able to know that this function will not be differentiable at this point. And once again, for review, what does this mean again? Not being differentiable? It means that the first principle, this limit cannot exist, because the limit in which x approaches a from the positive side and the limit of the first principle in which x approaches a from the negative side, or also can be interpreted as when h approaches 0 from the positive side and the limit when h approaches 0 from the negative side, will not be the same, not satisfying the conditions for this limit to exist. So therefore, that was a brief review. I thought it would be more shorter, but sorry for taking it a little too long. But that is the review for the basic limitual concepts for the identity of the first principles. Now, on the next class, we will be trying to go over more of the limitual concepts. However, that has been more, not the first principle itself, but the application from the first principles. And next class, I wouldn't say it will be required class, like the class that should be necessitated for you to listen to, because it may consider some of more extensive or difficult concepts. However, I still very much recommend you to learn and listen to the next lecture as well, because next lecture deals more about delicate and complex limitual concepts, which will literally allow you to grasp a more rigid understanding in the first principles. And I've said from the beginning of our the first class of our lecture, right? The first lecture, that this first principle, the strong comprehension, strong grasp of concept and the comprehension of the first principle will be the key for your success in the calculus course. So whatever choice you do, well, congratulations for listening to this class. I hope you review the materials that will make you stronger to listen to the next class. And again, thank you. Bye.